Only two more layers to go, transport and application. So in this video, I will provide you an overview of the transport layer. But first, do you remember what the transport layer does? Before we get into the role of the transport layer, here is a quick recap. We have reached quite a few milestones. We started out with a simple two-node network over a point-to-point link, and then we scaled it up to tens of nodes operating in a local area, and then we extended it to cover thousands of nodes, and then we interconnected heterogeneous networks to span millions of nodes. Right now, we know how to handle host-to-host delivery. You give a packet with the correct destination IP address. We know how to send it to the right destination. Basically, what happens is that the network layer determines which next hop to take along the path, and then it uses the services of the link layer to actually deliver the packet to the next hop, which in turn takes the services of the physical layer to convert the bits to signals to deliver the packet. But host-to-host delivery alone is not enough, because applications run as processes and a given host can have many processes, and we need to provide a method for process-to-process communication. So this is the role of the transport layer. As mentioned, a given host can run many applications. For example, on your own machine, if you run the top command in Unix, it will list a whole range of processes. By the way, not all of them are networking processes, but some processes you will see will be your web browsing processor, your email process, and then if you're running an SSH session, there'll be an SSH process, so on and so forth. So the transport layer's job is to provide logical communication between these processes. Let me emphasize on this word logical. What do I mean by this logical communication? Basically, the processes act as if they are directly connected with each other. They don't have to worry about the fact that in reality, there are many routers and link technologies interconnecting the hosts on which these processes are running. So this is kind of shown in this figure. So to the application process, this appears as a logical connection, but the path taken by the actual messages goes in this particular fashion to reach the other process. In providing logical communication, an important aspect to address is the multiplexing, demultiplexing of packets, that is delivering the packets to the right process. We touched upon this when we were covering the interlayer communication. So that's something the transport layer has to provide. In addition, the transport layer can enhance the network layer service. More on this shortly. The transport protocols are also called end-to-end protocols, since these are often implemented on the end hosts. So this is again captured here. So as you can see, they are implemented only on the end host and not in this intermediate routers. Again, a terminology issue. Henceforth, we will refer to a unit of data at the transport layer as a segment. So if you see in this figure, the transport layer is between the application layer and the network layer. It provides service to the application layer, and it itself takes service from the network layer. So to understand the role of the transport layer, it is useful to understand what the application requirements are and what kind of service the network layer provides. If you are an application developer writing code for, say, an email application or a file transfer application, as part of these applications, messages have to be delivered. How would you like these messages to be handled? So for example, I would like guaranteed delivery of messages, because I wouldn't like some portions of my email to be lost. The same applies for file transfer also. Can you think of two other application layer expectations? We touched upon this before. Depending on the type of the application, applications typically have certain expectations. So applications like email, file transfer, web browsing, many of these applications like guaranteed message delivery. They also like order delivery. Real-time applications expect delay guarantees. And again, you don't want any duplication to be done to your messages. Some applications would like support for arbitrarily large messages. In other words, would you like it if someone said keep your emails to under 5000 bytes? So applications like file transfer or email, you want to support arbitrarily large messages. Some applications may also want flow control. What do I mean by this is keeping track of the buffer space at the receiver so that the sending application doesn't overwhelm the receiver buffer space, thereby leading to loss of data. So these are application layer expectations, and then there is the network layer limitations. We have already seen that the IP layer provides best effort service. What can it do to packets sent to it? We have covered this before. Name at least 2 things it can do. Well, it can lose packets, it can reorder packets, it can duplicate packets, and it can also place certain restrictions on the message size. This arises from the MTU, which we have discussed before, and it can also delay the packets. As you can see, the expectations are totally contradictory to what the network layer can provide. So how should one meet the application layer expectations? One approach could be to tell the application, fine, this is the network layer service. If you want anything else, you build it yourself. But if many applications want the same kind of service, for example, this guaranteed message delivery is needed by many applications, email, file transfer, web browsing, so on and so forth, in which case it may be useful to implement this service as part of the communication infrastructure itself. So that's where the transport layer comes into play. The challenge at the transport layer is to enhance the network layer services to meet the application layer expectations. Note that you cannot provide services as part of the transport layer that inherently cannot be supported by the network layer. For example, the underlying networks do not support delay guarantees, then there is no way you can support delay guarantees as part of the transport layer. But some of these other features like reliable transport or duplicate packet suppression or in-order delivery can potentially be supported. So we have different transport protocols that offer different trade-offs, that is, they meet different application layer requirements. Note that unlike in IP, where there was a common protocol at the transport layer, we can support multiple protocols. User Datagram protocol is a very simple transport protocol. We will cover more of it shortly. Again, Transmission Control Protocol TCP is another transport protocol that provides reliable transfer, in-order delivery, so on and so forth. We will again look at it in more detail later. Remote procedure call is a transport mechanism that is used in distributed systems. As the name suggests, this refers to remote procedure calls. For example, when you're writing a program, you call certain procedures or functions, but often they are implemented as part of your own program. But if you want to implement certain procedures in some remote host, you need this particular mechanism. So as I said, this applies in distributed systems. And again, to cater to real-time applications, there is a real-time transport protocol. One point I should mention here is that for RPC as well as RTP, these both are developed over the UDP protocol. So some don't view these as protocols at the transport layer, they view this as protocols at the application layer, but that is not quite true because the mechanism that they are providing is logical communication between processes, which falls under the transport layer. We are anyway not going to cover these as part of this course. We'll focus only on UDP and TCP. A good time to break. Up ahead, we will look at multiplexing, demultiplexing, which is fundamental to any transport protocol. I have covered this aspect before, where the role of multiplexing, demultiplexing is to deliver the packet to the right process or protocol. So here we are focusing on the processes. So for this, you need special information to help the transport layer to deliver the segment to the right application process. And we have already seen that those fields are the source port and the destination port. Normally, you need the destination port based on which you are going to deliver it to the right process, but source port helps so that this process can communicate with the other endpoint. So any transport layer segment will have both these fields. So to understand how multiplexing, demultiplexing works, it is useful to know how a process interacts with the transport layer. So this interaction is via what is called a socket. So in Unix, one can view socket as a file descriptor. Basically, just like when you open a file, you get an integer associated with opening the file. Just like that, when you open a socket, you get a descriptor corresponding to that particular socket. And just like you write and read into a file, once you obtain a socket descriptor, the application process just sends and receives data to the other application process via this socket. So an application process writes into the socket, the transport layer takes the data and delivers it to the other end process, and the other end process reads from its corresponding socket. So we will cover more of this under socket programming. An application developer, when he is interfacing with a transport layer, he can potentially specify the type of transport protocol he wants to use, either UDP or TCP. And he could also configure a few parameters related to the particular transport protocol. For example, what segment size to use. So getting back to our original role of multiplexing, demultiplexing, to help multiplex or demultiplex a segment, you need to associate sockets with unique identifiers, and ports is definitely one of them. We'll see more of this soon. Not only that, the segments have to carry certain fields that help identify the right sockets. One fields of relevance here are the source and the destination port. There are two types of multiplexing, demultiplexing. One is called the connectionless multiplexing, demultiplexing. This is used with UDP sockets. In this particular case, a socket is identified by a two tuple, that is the destination IP address and the destination port number. So whenever the transport layer gets a packet, it looks at this information to decide which socket to send this packet to. So a point to note here is that IP datagrams with different source IP addresses and or source port numbers, but the same destination IP address and destination port number will be directed to the same socket, because you are not distinguishing based on source information. So the same thing is captured here. So there is blue process, red process running on two separate hosts, and they are sending this segments to the same destination port, thereby they get delivered to the same process. However, this application process knows to send it to different hosts because the source port information is different. Here it is 5000 and here it is 6000. Not only that, even if they were identical, it knows based on the source IP address when this packet came to redirect it to the correct destination host. I guess you may have some confusion that we are dealing with the transport layer, so we should focus only on ports, but often what happens is when you are passing a packet to the application layer, you also pass information on what the source of that particular packet is, the source IP as well as the source port is. These things will become clear once you start socket programming. This is happening because applications also need to know to who to deliver this particular messages to, which endpoint. And endpoints are typically characterized by IP addresses, apart from host names. So what we have seen so far is connection-less multiplexing, demultiplexing. There is connection-oriented multiplexing, demultiplexing as well. So this is used with TCP sockets. In this case, a socket is identified by a 4 tuple. Here you take into account the source IP address, source port, as well as the destination IP address and destination port. So basically, when you get a segment, you use all these fields to direct it to the right socket. So this is captured here. If you look at these two packets, as you can see, the source ports are the same, the destination ports are the same, the destination IP addresses are the same, but the source IP addresses are different. Thereby, they are being delivered to two separate processes. And similarly, if you look at this and this, all this information is the same. In other words, the source is the same, destination is the same, destination port is the same, but the source port information is different. Thereby, they are again being sent to two separate processes. All this is great, but something should be nagging in your head. How does one obtain the port information? In other words, how does this host know to set the destination port equal to 80? Often when we talk about process-to-process communication, there is a client and the server. A client is someone who initiates a connection to a given server. So when this client is initiating a connection, it can pick any random port as the source port and send this particular message. And once the server receives this particular message, it now knows the identity of the client process through this source IP address as well as the port information, the source port information that is. But how does the client know the server's port information? So this is similar to how do you know that you have to call number 100 to reach the police? It's a well advertised numbers, and this advertisement happens through other means. Similarly, well-known servers like the web server or the email server or the file transfer server listen to messages on well-advertised ports. So for example, in the Unix systems, the / etc. services will contain this information. In some applications, the well-known port is the starting point to agree upon some other port. What I mean is that to begin with, the client contacts the server on some well-known port P1, and as part of this message exchange between both of them, they negotiate that henceforth the client should contact this particular application on some other port P2. There is often some confusion on ports and sockets, so a quick note here. A server host can listen on designated ports, but it can have many sockets to support each incoming client. What do I mean by this? Let me give this example. Suppose there is a web server. It has opened a socket and it is associated the socket with port 80, and it is listening for incoming connections on this particular socket. Now when a client comes, this is the first message from that particular client, that is, this is the initial message being sent by the client. This web server is going to process this particular client information and open another socket to serve this particular client, and this socket will be associated with the source IP, source port, destination port, which is 80. This is also destination port 80, this is also destination port 80, and this is destination IP address. And the transport layer is configured such that it knows to direct the initial packets which are coming on port 80. So there is certain information in the TCP headers that says that this is the first packet for this particular client. It uses that information to direct all initial connections to this socket, but later packets of that particular client are directed to the correct socket. As you can see, the same port 80 is being associated with multiple sockets. In this particular case, whenever this web server sees a new client connection, it spawns a new process which is going to handle this new connection henceforth. So this new process listens on this particular socket. In this particular case, each process has a specific socket. So there's a one-on-one relation between both of them. This need not be the case. There are also cases where one process can have many sockets associated with it. This earlier case here typically slows down the server because you are spawning new processes for each incoming client connection. The more recent servers do threaded operation. In other words, for each new client, they spawn a new thread, but this is part of the same process. And this thread controls this particular socket. You do a bit of socket programming, all these points will become clear. So what have we learned in this video? The role of the transport layer is to provide logical communication. As part of it, an important feature is the multiplexing demultiplexing capability, that is delivering segments to the right application process. Apart from this, it could also try to enhance network services to meet certain application specific requirements. This leads to different types of transport protocols. In the context of multiplexing demultiplexing, we saw two types of multiplexing demultiplexing, connectionless and connection oriented, and we also saw the role the sockets play in enabling this.